So we now and we do this in such a way that the torsion obtained is the same. So now suppose we have a chain contraction. So what that means is we've got so this CK is going to denote this chain the first chain complex. So you've got the boundary map, you've got CK minus 1, dot dot dot, and you have a chain contraction, which is this map S going in the other direction. We've added two new cells to our chain complex via this elementary expansion, and we wish to define S on those cells. So what we do is we set S of En should be 0, and S of En minus 1 should give us En minus S of C, where C was this class here, which is the boundary minus this. Let me draw this over here, and we'll see that this gives a chain contraction. So we've got these two extra cells. We saw that the boundary map gives us +1, it gives us a copy of this, and it maps here and gives us C in here. And we've now defined S to go back the other way from here to here as +1, and in this direction as minus SC. So now we can just compose everything and just check that this works. Well, first of all, if we go from En to En minus 1 and back, we just get +1. If we go in the other way, like this gives us +1 as well. So far so good. And we want the net components going upwards to give us 0. So let's just look at those. If we go this way, that's C, and then if we go this way, that's minus SC followed by D, so that's minus DSC. So we get this, but because this is a chain contraction on the chain we already had to begin with, we can write this as SD of C, but D of C is 0 because we had the way C was defined. Is that right? Well, this should be 0. I'll think about it. And the other way, we have this plus this is we just get SC this way and we get minus SC the other way, which gives us 0. So I'll think about this later, but that should work. And this gives us a chain contraction. Now let's look at what happens to the torsion. So if n is even, then our new matrix for D plus S is, I need more space than this. So going from the even terms and also En, which is even, to the odd terms and En minus 1. So the matrix is, we just have D plus S, the original D plus S, from, was it odd to even? This might be the other way around. 0 here, this maps 1 there, and we also have C here. But this this has the same torsion as just D plus S, because we can obtain this C by elementary row operations from this 1. So this has same torsion as D plus S had before. And in the case that n is odd, we get the same thing happening, but instead of C we have this minus SC from the S component. So similarly for n odd. Okay, so this should justify that an elementary expansion, or conversely a contraction, doesn't change the torsion. So we've proved one direction, so simple homotopy equivalence as we've defined it just here, has torsion 0. And let's look at the converse direction. So to prove the converse, we require yet another result due to Whitehead, called Whitehead's cell trading lemma. So this states that if we have a CW pair, XY, a finite CW pair, with relative homotopy groups 0 up to dimension n, then there exists a simple homotopy equivalent x bar which is simple homotopy equivalent rel y, such that so x bar minus y has no cells of dimension less than or equal to n. What is this saying? It's saying that if we have a CW pair which is the inclusion is K connected, then you can, without loss of generality, you can take all the cells of dimension up to K to be in Y and none of them in X. The idea is that we can, if we have any that happen to be in X minus Y, we can trade them up for a cell of dimension 2 greater, and you can do this up to dimension n here. So let me sketch how this goes. And then this lemma will allow us to prove the converse direction. So the proof if we have an I cell in x minus y for I less than or equal to n, this can be traded for an I plus 2 cell in x bar minus y. Where we go via so we introduce these cancelling cells, and then we cancel this with the one we didn't want in x minus y, and this leaves just one in x bar minus y. So this is exactly the same idea as we had for handle cancellation. So then we contract this and the cell we didn't want here to get x bar.